In the depths of space where no human eye will ever gaze and no instrument will ever reach, there exists a number that defines the ultimate destiny of everything we have ever known. -273.15 degrees Celsius. This is absolute zero, the temperature at which atomic motion ceases, where thermal energy becomes zero, where the universe itself would fall into perfect, eternal stillness. Right now, as you read these words, the cosmos around us maintains an average temperature of 2.7 Kelvin, barely 2.7 degrees above that absolute threshold. This ambient warmth, a faint echo of the Big Bang, fills every cubic centimeter of space between galaxies. It is the universe's pulse, its last vital sign. But this temperature is falling. It has been falling for 13.8 billion years, and it will continue to fall until it approaches that final, terrible number. The timeline stretches before us like an abyss, 10 to the power of 100 years. To comprehend this span, imagine that every atom in the observable universe, roughly 10 to the power of 80 of them, was itself an entire universe containing 10 to the power of 80 atoms. The total number of particles in this unimaginable hierarchy would still fall short of the years required for the universe to reach its final, frozen state. Yet absolute darkness means more than cold. It represents the moment when the last black hole evaporates into elementary particles, when the final photon of light travels its lonely path through empty space, when entropy reaches its mathematical maximum and time itself loses all meaning. In this future, no observer will remain to witness the darkness. No consciousness will exist to contemplate the silence. The universe will have become a vast, uniform sea of elementary particles, separated by distances so enormous that they might as well be alone in infinite space. This is not science fiction. This is thermodynamics, the most tested, most reliable branch of physics ever developed. The equations that predict this cosmic ending are the same ones that govern the cooling of your coffee, the operation of your refrigerator, the burning of stars. They are laws so fundamental that they have never been observed to fail, not once, in any system ever studied. But what does this ultimate ending truly mean for consciousness, for meaning, for the very possibility of existence itself? The answer lies not in distant futures, but in discoveries made right here, right now, by scientists who dared to peer into the mathematical heart of reality and found there not eternal paradise, but cosmic mortality on a scale that dwarfs human comprehension. The story of absolute darkness begins on a cold winter day in 1850 in the German city of Berlin, where a young physicist named Rudolf Julius Emanuel Clausius sat hunched over his desk, struggling with a problem that seemed almost trivial. Why does heat always flow from hot objects to cold ones, never the reverse? Clausius had been studying the work of Sadi Carnot, a brilliant French engineer who had analyzed the efficiency of steam engines. Carnot had discovered that no engine could be perfectly efficient. Some energy was always lost as waste heat. But Carnot's work was incomplete, and Clausius sensed that hidden within these observations lay a principle so profound it would reshape humanity's understanding of existence itself. Working through the mathematics of heat flow, Clausius formulated what would become known as the second law of thermodynamics. In its simplest form, the law states that heat always flows from hot to cold, never the reverse, in any isolated system. But Clausius saw deeper implications. He realized that this process was fundamentally irreversible. Once energy had been dispersed, it could never spontaneously concentrate again without external intervention. The implications terrified him. If the universe was indeed an isolated system, if there was no external source of energy to reverse the flow of heat, then all the energy in the cosmos was slowly but inexorably spreading out, becoming more and more diffuse, until eventually everything would reach the same temperature. When that happened, no further energy could flow, no work could be done, and all processes would cease forever. In 1865, Clausius gave this tendency toward disorder a name drawn from Greek, entropy, meaning transformation. He concluded his landmark paper with a statement that would echo through physics for centuries. The energy of the universe is constant. The entropy of the universe tends to a maximum. Word of Clausius's discovery reached William Thomson, later Lord Kelvin, at the University of Glasgow. Kelvin was already famous for his work on absolute zero, the theoretical temperature at which all thermal motion would cease. But Clausius's entropy concept hit him like a physical blow. If entropy always increased, if energy always dispersed, then the universe was not eternal, it was dying. On April 19, 1862, Kelvin presented a paper to the Royal Society of Edinburgh that would haunt him for the rest of his life. He calculated that the sun was radiating energy into space at a tremendous rate, energy that would never return. Based on the known laws of physics, the sun had perhaps 20 to 40 million years of fuel remaining. The Earth would freeze, all life would end. And eventually, every star in the universe would exhaust its fuel and die, leaving behind a cold, dark cosmos. But Kelvin's calculations were based on gravitational contraction as the sun's energy source. He didn't know about nuclear fusion, which would extend the sun's lifetime to about 10 billion years. He couldn't have imagined that his prediction was actually optimistic, that the universe's fate was far more absolute than even he had dared to contemplate. The next breakthrough came from Hermann von Helmholtz in Berlin. In 1867, Helmholtz extended the thermodynamic analysis to the entire universe. He described a final state of thermal equilibrium, where all matter would be at the same temperature, where no energy could flow, where all motion would cease except for the random thermal vibrations of atoms approaching absolute zero. Helmholtz's vision was mathematically precise and existentially devastating. The universe was not just mortal, it was mathematically required to die. Every process, every thought, every moment of consciousness was contributing to the inexorable increase in entropy that would eventually render all future action impossible. The mathematical framework was refined by James Clerk Maxwell, Ludwig Boltzmann, and Willard Gibbs. Maxwell showed that entropy was related to the statistical arrangement of molecules, that ordered states were vastly outnumbered by disordered ones. Boltzmann developed the statistical mechanics that made this relationship precise, showing that the tendency toward maximum entropy wasn't just probable, it was inevitable on cosmic scales. Boltzmann himself struggled with the implications of his own work. The universe, according to his equations, had evolved from an improbably ordered initial state, the Big Bang, and was condemned to evolve toward maximum disorder. Every moment of existence was borrowed time, stolen from the universe's inexorable march toward equilibrium. The emotional toll on these early pioneers was severe. Lord Kelvin, despite having helped establish the mathematical foundation for universal death, spent years searching for loopholes. He proposed that gravitational collapse might somehow regenerate heat, that unknown forces might restore the universe's vitality. But his own equations suggested otherwise. Maxwell wrote to Lord Rayleigh in 1870, "The second law of thermodynamics has the same degree of truth as the statement that if you throw a tumblerful of water into the sea, you cannot get the same tumblerful out again." The analogy was precise and terrifying. The universe's usable energy was being thrown into the sea of space, never to be recovered. The discovery of universal expansion by Edwin Hubble in 1929 added a cruel twist to the story of cosmic death. Not only was the universe's energy spreading out through thermodynamic processes, space itself was expanding, carrying galaxies away from each other and further diluting the cosmic energy density. The universe wasn't just running down, it was actively dispersing its contents across ever greater volumes. NTHE detection of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965 provided direct confirmation of cosmic cooling. Their measurements showed that the universe was filled with electromagnetic radiation at a temperature of 2.7 Kelvin, the cooled remnant of the Big Bang's intense heat. This radiation was cooling as space expanded, and would continue cooling toward absolute zero as the universe aged. Stephen Hawking's 1974 prediction of black hole evaporation added the final haunting chapter to the story of cosmic death. Even black holes, those gravitational monsters that seemed eternal, would eventually disappear through quantum effects. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to evaporate completely through Hawking radiation. More massive black holes would take even longer, but eventually, every black hole in the universe would vanish, leaving behind only a dilute gas of elementary particles drifting through ever-expanding space. The scientific community's reaction to heat death theory was nothing short of existential crisis. Here was a prediction that emerged not from philosophical speculation or religious doctrine, but from the most fundamental and well-tested laws of physics. The mathematics were elegant, the logic was airtight, and the conclusion was inescapable. The universe was mortal. The initial resistance was fierce and deeply personal. Scientists who had devoted their lives to understanding nature suddenly found themselves confronting the ultimate meaninglessness of their work. If the universe was destined for maximum entropy, if all complexity would eventually dissolve into uniform disorder, then what was the purpose of knowledge itself? Einstein's initial reaction was to reject the implications entirely. When his field equations of general relativity predicted an expanding or contracting universe, he added the cosmological constant, a mathematical term that would allow for a static, eternal cosmos. The idea of a dying universe was so philosophically unacceptable that Einstein was willing to modify his most successful theory to avoid it. The introduction of such a constant implies a considerable renunciation of the logical simplicity of the theory, Einstein wrote in 1917. But he believed the alternative, a universe with a beginning and end, was worse than mathematical inelegance. He would later call the cosmological constant his greatest mistake, but not because it was wrong mathematically. He regretted it because it prevented him from predicting the universe's expansion before Hubble's observations confirmed it. Fred Hoyle, the brilliant British astronomer, spent decades developing the steady-state theory of cosmology specifically to avoid the implications of cosmic death. Hoyle proposed that the universe was eternal and unchanging on large scales, with new matter continuously created to maintain constant density as space expanded. The steady-state theory was mathematically sophisticated and observationally viable through the 1950s. But Hoyle's theory required continuous creation of matter from nothing, a violation of conservation of energy so fundamental that it demanded radical revision of physical laws. Even Hoyle recognized the desperation in his proposal. He once said, "The universe is not only stranger than we imagine, it is stranger than we can imagine." Yet he couldn't accept that this strangeness included universal mortality. NTHE philosophical implications went far beyond physics. Victorian society was already grappling with Darwin's theory of evolution, which had removed humans from their special place in creation. Now thermodynamics suggested that not only were humans insignificant in space, they were insignificant in time as well. Every civilization, no matter how advanced, would eventually succumb to the universal trend toward maximum entropy. Religious leaders joined the debate, often arguing that divine intervention would prevent cosmic death. But scientists had learned to be skeptical of arguments that required supernatural explanations for natural phenomena. The second law of thermodynamics had been tested in countless experiments, from steam engines to chemical reactions to stellar observations. It had never failed, not once. NTHE mathematical certainty was what made the predictions so disturbing. Unlike other theoretical frameworks that required uncertain assumptions or unproven physics, heat death emerged directly from the most fundamental and well-tested principles in science. The equations were simple enough for undergraduate students to understand, yet their implications were profound enough to challenge every assumption about meaning and purpose in the universe. Boltzmann himself suffered from severe depression, which some historians have linked to the existential implications of his statistical mechanics. He had shown that the approach to maximum entropy wasn't just probable, it was mathematically inevitable given enough time. The universe was already dying, had always been dying, and there was nothing anyone could do to prevent it. The paradox was particularly acute for consciousness itself. Here were conscious beings, the products of 13.8 billion years of cosmic evolution, using their intelligence to discover their own ultimate insignificance. The universe had become aware of itself just in time to realize that this awareness was temporary, that consciousness itself was a brief anomaly in the cosmos's journey toward maximum entropy. Perhaps most disturbing was the realization that heat death violated human intuitions about time and causality. People could accept that individual stars died, just as they could accept that individual organisms died. But the idea that time itself might become meaningless, that in the far future there would be no way to distinguish one moment from another because nothing would be changing, challenged fundamental assumptions about the nature of existence. The numbers themselves were incomprehensible. When physicists calculated the timeline of cosmic death, they confronted figures so vast that they defied human understanding. The Sun would die in about 5 billion years, still within geological timescales. But true heat death would occur on timescales that made the current age of the universe seem like an instant. Consider the progression that emerged from 20th century physics. After the last star dies in about 100 trillion years, the universe enters the degenerate era, populated only by stellar remnants, white dwarfs, neutron stars, and black holes. But even these objects are temporary. Protons themselves, the building blocks of ordinary matter, are predicted to decay with a half-life of about 10 to the power of 34 years. This means that in 10 to the power of 40 years, even the atoms that compose dead planets and stars will have disintegrated into elementary particles. The black hole era follows, lasting from 10 to the power of 40 to 10 to the power of 100 years. During this unimaginably long period, black holes are the only remaining objects of significant mass. They slowly evaporate through Hawking radiation, with the most massive ones taking the longest to disappear. A black hole with the mass of our galaxy would take about 10 to the power of 99 years to completely evaporate. Finally comes the dark era, when only elementary particles remain, separated by distances so vast that they rarely interact. The universe approaches maximum entropy, with temperature approaching absolute zero and no possibility of further organized activity. As observational astronomy advanced through the 20th century, the theoretical predictions of cosmic death began to find direct confirmation in the data streaming back from telescopes and space missions. What scientists discovered was not just evidence for universal mortality, but signs that the dying process was already well underway. Stellar spectroscopy, pioneered by Annie Jumpcannon and Cecilia Payne at Harvard Observatory, revealed the life cycles of stars with unprecedented clarity. By analyzing the light from thousands of stars, astronomers could determine their masses, temperatures, ages, and remaining lifetimes. The results confirmed the thermodynamic predictions. Every star was burning through a finite fuel supply, converting hydrogen into heavier elements and radiating the released energy into space. More disturbing was the discovery that star formation rates were declining throughout the universe. Surveys of galactic populations showed that the cosmos had been more active in the past. The peak of star formation occurred about 11 billion years ago, when the universe was only 2.8 billion years old. Since then, the rate had been steadily declining as galaxies exhausted their supplies of star-forming gas. Edwin Hubble's 1929 discovery of universal expansion provided the final piece of evidence for cosmic cooling. Hubble's measurements of galactic recession velocities showed that space itself was expanding, carrying galaxies away from each other and stretching the wavelengths of light traveling between them. This expansion meant that the cosmic microwave background radiation, the afterglow of the Big Bang, was continuously cooling as the universe aged. The Hubble constant, measuring the rate of cosmic expansion, was initially calculated at about 500 kilometers per second per megaparsec, a value that would have made the universe younger than the Earth. Subsequent refinements brought the value down to about 70 kilometers per second (MPC), giving the universe an age of approximately 13.8 billion years. But regardless of the precise number, The expansion confirmed that the universe was cooling toward absolute zero. Observations of globular clusters, ancient collections of stars that formed in the early universe, revealed stellar populations that were already well into their death throes. Many globular clusters contained large numbers of white dwarf stars, the cooling remnants of stars that had exhausted their nuclear fuel. These white dwarfs were slowly radiating away their remaining heat, approaching the cold, dark fate that awaited all stellar matter. The discovery of the cosmic microwave background by Penzias and Wilson in 1965 provided direct measurement of the universe's current temperature. At 2.725 Kelvin, the CMB represented the cooled remnant of the Big Bang's initial heat. More importantly, precision measurements showed that this temperature was falling as the universe expanded, confirming the theoretical prediction of approach toward absolute zero. Radio astronomy revealed another disturbing trend: the increasing dominance of dead and dying stellar objects. Surveys of radio sources showed that the universe was becoming populated by neutron stars, white dwarfs, and black holes, the endpoints of stellar evolution. These objects contributed to the cosmic inventory of mass and energy, but they were no longer generating new light or heat. They were cosmic fossils, monuments to processes that had already ended. X-ray observations from early space missions detected the signatures of matter falling into black holes, the most efficient entropy generators in the universe. As matter spiraled into these gravitational wells, it was heated to millions of degrees and radiated its energy away as X-rays. This process was irreversible. Once matter crossed a black hole's event horizon, its information and energy were effectively lost to the outside universe forever. Perhaps most sobering were the observations of planetary nebula, the glowing shells of gas expelled by dying stars. These beautiful structures, illuminated by the hot white dwarf remnants at their centers, represented the final act of stellar death. The gas would eventually disperse into interstellar space, becoming too dilute to form new stars, while the central white dwarf would slowly cool toward absolute zero over trillions of years. But if the mathematics of cosmic death were this precise, this unavoidable, then the instruments that would soon peer deeper into space and time were about to reveal something that would make heat death seem like merely the opening act of a far more complex and disturbing cosmic drama. On April 24, 1990, the Space Shuttle Discovery lifted off from Kennedy Space Center, carrying humanity's most ambitious attempt to witness cosmic death in real time. The Hubble Space Telescope, freed from the blurring effects of Earth's atmosphere, would soon begin transmitting images that would fundamentally alter our understanding of universal mortality. Hubble's first deep field observations, released in 1996, revealed something unprecedented. Galaxies stretching back to within a billion years of the Big Bang, their light having traveled for over 12 billion years to reach us. But these ancient galaxies appeared surprisingly mature and well-formed, suggesting that the universe's transition from chaos to order and its inevitable return to disorder had proceeded faster than anyone had imagined. The Hubble Deep Field contained approximately 3,000 galaxies in a patch of sky no larger than a grain of sand held at arm's length. When astronomers calculated the total number of galaxies visible to Hubble throughout the observable universe, they arrived at a staggering figure: over 100 billion galaxies, each containing hundreds of billions of stars. Yet follow-up observations revealed that star formation in these galaxies had peaked 11 billion years ago and had been declining ever since. Dr. Piero Madao of the University of California, Santa Cruz, published the definitive study in 1996, showing that the cosmic star formation rate was now only about 1/10 of its peak value. The universe had already consumed most of its star-forming fuel. "We're living in the aftermath of the cosmic baby boom," Madao observed. "The universe's most creative period is behind us." But Hubble's observations revealed something even more disturbing than declining star formation. The telescope could directly observe stellar death in unprecedented detail. Images of planetary nebulae showed the final moments of sun-like stars, their outer layers expelled into space as they evolved into white dwarfs. More dramatically, Hubble captured supernova explosions. the violent deaths of massive stars that briefly outshone entire galaxies before fading into darkness. The Cosmic Background Explorer, COBE, launched in 1989, provided the first precision measurements of the universe's background temperature. COBE confirmed that the cosmic microwave background radiation was exactly 2.725 Kelvin, with tiny variations that revealed the seeds of cosmic structure. But more significantly, COBE's measurements showed that this temperature was falling according to precise mathematical predictions as space expanded. Dr. John Mather, COBE's principal investigator, realized that they were witnessing cosmic cooling in real time. Every measurement we make shows the universe getting colder, Mather noted. We're watching entropy increase on the largest possible scale. The most shocking discovery came in 1998, when two independent teams studying distant supernovae made an observation that defied all expectations. The Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University, had been measuring the expansion rate of the universe by observing Type Ia supernovae at various distances. These supernovae served as standard candles, astronomical objects with known intrinsic brightness that could be used to measure cosmic distances. By comparing their apparent brightness with their known luminosity, astronomers could determine how far away they were. By measuring their redshift, they could determine how fast they were receding due to cosmic expansion. What they found contradicted every model of cosmic evolution. Instead of slowing down due to gravitational attraction, the universe's expansion was accelerating. Distant supernovae appeared dimmer than expected, indicating they were farther away than predicted by models of decelerating expansion. NTHE implications were staggering. Some unknown form of energy, dubbed dark energy by Michael Turner, was pushing space apart with increasing strength. This energy constituted approximately 68% of the universe's total energy density, yet it was completely invisible and interacted with matter only through its gravitational effects. NDR. Adam Rees, a member of Schmidt's team, described the moment of discovery. It was like throwing a ball up in the air and watching it accelerate upward instead of falling back down. We checked and rechecked our data because the result was so unexpected. The Planck satellite, launched in 2009, refined these measurements with extraordinary precision. Planck's observations of the cosmic microwave background revealed that dark energy constituted exactly 68.3% of the universe's energy density, with dark matter accounting for 26.8% and ordinary matter only 4.9%. The universe was dominated by mysterious components that seemed designed to accelerate cosmic death, and Planck's data also revealed that the universe's geometry was flat to within 0.4% accuracy, confirming that expansion would continue forever. There would be no big crunch to reverse the increase in entropy. The universe was committed to eternal expansion and cooling toward absolute zero. NTHE Large Hadron Collider, which began operations in 2008, provided disturbing insights into the fundamental stability of space itself. The discovery of the Higgs boson in 2012 allowed physicists to calculate the properties of the Higgs field that gives particles their mass. The results suggested that our universe might exist in a metastable state, stable for now but capable of transitioning to a lower energy configuration. Dr. Joseph Liken of Fermilab calculated that the measured mass of the Higgs boson, 125.18 billion electron volts, placed the universe precariously close to the boundary between stability and instability. The universe wants to be in a different state, Liken explained, and it's possible that we're living in a false vacuum that could decay at any moment. The Laser Interferometer Gravitational Wave Observatory, LIGO, achieved first detection of gravitational waves in September 2015, observing the merger of two black holes approximately 1.3 billion light-years away. The detection confirmed Einstein's century-old prediction, but it also revealed that the universe was losing energy through gravitational radiation. Every orbital system, from binary stars to planets around their suns, slowly loses energy by emitting gravitational waves. The process is extremely slow for systems like Earth orbiting the Sun, but it's inexorable. Given enough time, every bound system in the universe will decay through gravitational wave emission, NDR. Kip Thorne, LIGO's theoretical architect, observed, "We're detecting the universe's slow-motion dissolution. Every merger we observe represents irreversible energy loss, another step toward maximum entropy." The James Webb Space Telescope, launched on December 25, 2021, provided the most detailed view yet of cosmic death processes. Webb's infrared capabilities allowed it to observe the coolest objects in the universe: brown dwarfs, stellar remnants, and the dust clouds where stars are born and die. Webb's observations of brown dwarfs revealed billions of these failed stars throughout the galaxy. These objects, too small to ignite nuclear fusion, represent the universe's future. Cold, dark remnants slowly cooling toward absolute zero. Webb could measure their temperatures with unprecedented precision, providing direct calibration for models of cosmic cooling. As the 21st century progressed, each new observation seemed to reveal that the universe was dying faster than predicted. The discovery of dark energy had already shown that expansion was accelerating, but subsequent measurements suggested something even more disturbing. Dark energy itself might be growing stronger over time. The Dark Energy Survey, conducted from 2013 to 2019 using the Dark Energy Camera at the Cerro Tololo Inter-American Observatory in Chile, mapped over 300 million galaxies to measure the effects of dark energy across cosmic history. The results suggested that dark energy's equation of state parameter, designated as QO, might be less than -1. In conventional cosmology, W equals -1 corresponds to Einstein's cosmological constant, a fixed energy density of empty space. But if W less than -1, it implies phantom dark energy that grows stronger as the universe expands. This scenario would lead to a big rip, where dark energy eventually overcomes all other forces, tearing apart galaxies, stars, atoms, and ultimately space-time itself. Dr. Robert Caldwell of Dartmouth College, who first proposed phantom dark energy in 2002, calculated the timeline. If W is significantly less than -1, the Big Rip could occur in about 22 billion years, long before classical heat death, but still within a finite time. The timeline of the Big Rip was terrifyingly precise. First, about 1 billion years before the end, galaxies would be ripped apart as dark energy overcame gravitational binding. Then, 60 million years before the end, our solar system would dissolve as planets were torn from their orbits. Finally, in the last fraction of a second, atoms themselves would be shredded as phantom energy overcame electromagnetic and nuclear forces. NOB observations from the European Space Agency's Planck mission provided additional evidence for accelerating cosmic death. Planck's measurements of the cosmic microwave background revealed subtle patterns that suggested dark energy's influence had been growing stronger throughout cosmic history. The data indicated that what we observe as dark energy today might be different from what existed in the early universe. Dr. George F. Stathio of Cambridge University, a member of the Planck team, noted, "The data suggests that dark energy is not a simple cosmological constant. Its properties appear to be evolving, and that evolution seems to be accelerating the universe's approach to its final state." NTHE discovery that star formation was declining faster than expected added another layer of urgency to cosmic death scenarios. The Galaxy Evolution Explorer, GALEX, an ultraviolet space telescope that operated from 2003 to 2013, surveyed star formation rates in thousands of galaxies across cosmic time. NG-ALEX observations showed that the cosmic star formation rate had declined by a factor of 10 since its peak 11 billion years ago, but the decline was accelerating. Galaxies were running out of star-forming gas faster than expected, while dark energy's expansion prevented them from acquiring new material from intergalactic space. Dr. Christopher Martin of Caltech, GALEX's principal investigator, observed, We're witnessing the universe's transition from a star-forming phase to a post-stellar phase. The era of cosmic creativity is ending ahead of schedule. The Large Hadron Collider's measurements of the Higgs field raise the specter of vacuum decay, a process that could end the universe almost instantaneously. If the Higgs field exists in a metastable state, random quantum fluctuations could trigger a transition to the true vacuum. This would create a bubble of space with different physical laws expanding at light speed, destroying all matter in its path. NDR. Pier Paolo Giardino of CERN calculated the probability. The chance of vacuum decay is extremely small in any given year, perhaps 1 part in 10 to the power of 100. But over the 10 to the power of 100-year timescale of cosmic evolution, it becomes virtually certain. Gravitational wave observations revealed that black hole mergers were occurring more frequently than predicted, accelerating the universe's evolution toward maximum entropy. Each merger converted about 3 to 5% of the total mass into gravitational waves, energy permanently lost to the cosmic inventory. The Event Horizon Telescope's first images of black holes, M87 Scarus in 2019 and Sagittarius A* in 2022, provided direct views of matter falling into these ultimate entropy generators. The images showed the characteristic shadow of the event horizon, surrounded by the glowing accretion disk of doomed matter. Dr. Shepard Doelman, EHT's founding director, reflected, "We're seeing matter's point of no return. Once it crosses that event horizon, its information and energy are lost to the outside universe forever." These black holes are cosmic vacuum cleaners, and they're accelerating the universe's approach to maximum entropy. Faced with mounting evidence of accelerated cosmic death, theoretical physicists proposed increasingly sophisticated models to explain the universe's fate. Each theory painted a different picture of the end, but all agreed on one fundamental point. The universe's destiny was determined by its own physical laws, and those laws were inexorably driving it toward a state of maximum entropy. Phantom dark energy theory emerged from attempts to explain the observed acceleration of cosmic expansion beyond what a simple cosmological constant could produce. Developed by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg in 2002, this theory proposed that dark energy was not constant but grew stronger over time. NTHE mathematics were elegant but terrifying. Phantom energy has an equation of state W less than -1, meaning its density increases as the universe expands, the opposite of normal matter and energy, which become diluted by expansion. As phantom energy grows stronger, it eventually overcomes all other forces in a finite time, causing the scale factor of the universe to diverge to infinity. The Big Rip scenario proceeds with mathematical precision. Approximately 22 billion years from now, phantom energy density would reach a critical threshold where it overcomes gravitational binding on all scales. Galaxy clusters would dissolve first, followed by individual galaxies, then solar systems, then planets, and finally atoms themselves. The process would culminate in a finite time when space-time itself is torn apart. Dr. Caldwell calculated the final moments. In the last 10 to the power of -19 seconds before the Big Rip, even atomic nuclei would be torn apart. The universe would end not with a whimper, but with the most violent event possible, the destruction of space-time itself. Vacuum decay theory offered an even more immediate threat to cosmic existence. Based on quantum field theory and the measured properties of the Higgs boson, this theory suggested that our universe exists in a false vacuum, a local minimum of energy that appears stable but could suddenly transition to a lower state. And Sidney Coleman and Frank DeLucia developed the mathematical framework in 1977, showing that if the Higgs potential has the right shape, quantum tunneling could create a bubble of true vacuum that expands at light speed. Inside this bubble, the laws of physics would be fundamentally different. Electrons might become unbound from nuclei, the strong nuclear force might weaken, or the constants governing matter might change completely. NTHE bubble wall would be completely invisible and instantaneous from our perspective. We would have no warning of its approach, and no possibility of escape. One moment we would exist under current physical laws, The next, we would be annihilated by different physics entirely. Dr. Joseph Likens' 2012 calculations based on LHC measurements suggested the probability of vacuum decay was extremely low, but non-zero. The universe could end tomorrow through vacuum decay, Liken observed, or it might be stable for 10 to the power of 100 years. The quantum mechanics makes it impossible to predict when it might happen. Encyclic cosmological models attempted to offer hope by suggesting the universe might undergo infinite cycles of expansion and contraction. Developed by Paul Steinhardt of Princeton and Neil Turok of Cambridge, these models proposed that what we observe as the Big Bang was actually just one event in an endless series of cosmic cycles. In the ekpyrotic scenario, our universe periodically collides with a parallel brane, a higher dimensional membrane, triggering a new Big Bang and resetting cosmic evolution. This would allow the universe to avoid heat death by periodically returning to a low entropy state. But even cyclic models couldn't escape the second law of thermodynamics. Each cycle would necessarily produce more entropy than the previous one, meaning the cycles couldn't continue forever. Eventually, even a cyclic universe would reach maximum entropy and cease to cycle. Dr. Steinhardt acknowledged the limitation. Cyclic cosmology can extend the universe's lifetime enormously, but it can't make it truly eternal. The second law of thermodynamics ultimately wins. Most advanced instruments are now directly observing the mechanisms of cosmic death with unprecedented precision. Each new mission and observatory brings greater detail to our understanding of universal fate, while simultaneously revealing new pathways towards string theory contributions to cosmic death, focused on the behavior of fundamental strings in low-energy environments. In the far future, when the universe approaches maximum entropy, thermal fluctuations become extremely weak. This might cause strings to undergo phase transitions to more stable configurations, fundamentally altering the properties of matter and energy. Some string theorists propose that the universe might have multiple vacuum states, each with different physical constants and particle masses. Random quantum fluctuations could cause transitions between these states, creating pocket universe with different laws of physics scattered throughout spacetime. NDR. Leonard Susskind of Stanford developed the string landscape concept, suggesting that our universe might be just one of 10 to the power of 500 possible vacuum states. While this offered the possibility of cosmic renewal through vacuum transitions, it also meant that each state would eventually decay to others, contributing to overall entropy increase. Information theory added a paradoxical dimension to cosmic death scenarios. If information cannot be destroyed, as quantum mechanics suggests, then what happens to all the information in the universe when it reaches maximum entropy? This question became acute with Hawking's discovery that black holes evaporate, apparently destroying the information that falls into them. NTHE, black hole information paradox, suggested that either quantum mechanics or general relativity must be wrong, since they seem to make contradictory predictions about information conservation. Some theorists proposed that information might be preserved in subtle correlations between particles, even at maximum entropy. Others suggested that information might somehow escape the universe entirely during black hole evaporation, NDR. Leonard Susskind and Gerard T. Hooft developed the holographic principle, suggesting that all information in a volume of space might be encoded on its boundary. This could allow information to survive even the complete evaporation of black holes, but it would still leave the question of what happens to information in a maximally entropic universe. Modern science's absolute darkness that earlier theories hadn't anticipated. NTHE Dark Energy Spectroscopic Instrument, DESI, which began operations in 2021, represents humanity's most ambitious attempt to map the accelerating expansion of the universe. Located at Kitt Peak National Observatory in Arizona, DESI can simultaneously observe 5,000 galaxies, measuring their distances and recession velocities, to create a three-dimensional map of cosmic structure across 11 billion years of history. DESI's primary mission is to determine whether dark energy is truly constant or evolving over time. The instrument will map 35 million galaxies and 2.4 million quasars, measuring the expansion rate at different epochs with unprecedented precision. If dark energy is strengthening, if W less than -1, DESI should detect the signature in the data, NDR. Julian Guy of Lawrence Berkeley National Laboratory, DESI's Data Analysis Coordinator, explained the implications. If we confirm that dark energy is phantom energy, it changes everything. Instead of heat death in 10 to the power of 100 years, we're looking at cosmic destruction in about 22 billion years. NTHE European Space Agency's Euclid mission, launched in July 2023, approaches the dark energy problem from a different angle. Euclid measures weak gravitational lensing, the subtle distortion of galaxy shapes caused by intervening dark matter and dark energy. These measurements provide independent confirmation of expansion history and dark energy properties. Euclid's wide-field surveys will cover 15,000 square degrees of sky, observing billions of galaxies with extraordinary precision. The mission's goal is to measure dark energy's equation of state parameter W to within 2% accuracy, definitively determining whether phantom dark energy threatens cosmic stability. NTHE Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will conduct the most comprehensive supernova survey in history. Roman will observe thousands of Type Ia supernovae across cosmic time, measuring the expansion history with unprecedented accuracy. The mission will also conduct microlensing surveys to search for dark matter and study the formation of the first stars. Dr. Jeffrey Crook, Roman's project scientist, noted, Roman will either confirm that we live in a universe dominated by phantom dark energy heading for a big rip, or it will reveal new physics that changes our understanding of cosmic fate entirely. In-ground-based observatories are also contributing to our understanding of cosmic death. The Cosmic Microwave Background Stage 4 (CMBS-4) experiment, planned for deployment in the 2030s, will measure the polarization of the cosmic microwave background with exquisite sensitivity. These measurements can detect primordial gravitational waves from cosmic inflation and provide new insights into dark energy's properties. NCMBS-4 will deploy over 500,000 detectors at sites in Antarctica and Chile, achieving sensitivity levels that seemed impossible just decades ago. The experiment will measure the cosmic microwave background temperature to micro-Kelvin precision, directly observing the universe's cooling in real time. NP particle physics experiments are probing vacuum stability with increasing sophistication. The High Luminosity Large Hadron Collider, HLLHC, scheduled to begin operations in 2029, will collect 10 times more data than the current LHC. This increased statistics will allow precise measurements of the Higgs boson's self-coupling, the parameter that determines vacuum stability. Underground detectors searching for proton decay continue to push sensitivity limits. The Deep Underground Neutrino Experiment, DUNE, under construction in South Dakota, will search for proton decay with unprecedented sensitivity. A positive detection would confirm that ordinary matter is fundamentally unstable, validating grand unified theories that predict atomic disintegration long before black hole evaporation. And future gravitational wave observatories promise to revolutionize our understanding of cosmic death processes. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves from space, observing the merger of supermassive black holes across cosmic history. NLISA will measure the rate at which the universe's most massive objects are consolidating through mergers, providing direct observation of cosmic simplification. Each detected merger represents a step toward the black hole era, when these objects will be the only remaining sources of organized energy in the universe. NTHE Einstein Telescope, a proposed third-generation ground-based gravitational wave detector, would achieve sensitivity levels that could observe black hole evaporation directly through Hawking radiation. While the signals would be extremely weak, the telescope's advanced design might make detection possible for the first time, Supercomputer simulations now model cosmic evolution from the Big Bang through heat death with extraordinary detail. The Millennium Simulation series, running on some of the world's most powerful computers, tracks the evolution of dark matter, ordinary matter, and dark energy across billions of years. These simulations consistently show accelerating approach toward maximum entropy, with no mechanism for reversal or escape. The largest simulations now model volumes containing billions of galaxies, tracking their evolution through star formation, stellar death, black hole growth, and eventual dispersal by dark energy, NDR. Volker Springel of the Max Planck Institute for Astrophysics, who leads the Millennium Project, observed, "Every simulation we run shows the same result. The universe is evolving inexorably toward a state of maximum entropy. We can vary the initial conditions, change the dark energy properties, modify the physics, but the endpoint is always the same." Yet as these instruments pushed the boundaries of observation to their absolute limits, they began to detect something in the quantum realm. Subtle signatures that suggested the journey to absolute darkness might not end in the peaceful emptiness that physicists had imagined, but in something far more profound and mysterious. In the deepest laboratories beneath CERN, where the Large Hadron Collider accelerates it manifests as the smallest possible deviation from perfect symmetry, a quantum fluctuation so subtle that it requires the collision of trillions of particles to glimpse even once. Yet this microscopic anomaly may hold the key to understanding what truly happens when the universe reaches absolute darkness. The discovery emerged from precision measurements of the Higgs field self-interaction, conducted during the LHC's Run-3 operations beginning in 2022. Dr. Giulia Zandarighi of Oxford University, analyzing data from the ATLAS detector, noticed that the Higgs boson's decay patterns showed infinitesimal deviations from standard model predictions. The deviations occurred only in the highest energy collisions, when the Higgs field was pushed far from its equilibrium state. "We're seeing something that shouldn't exist according to our current understanding," Zandarighi reported to the particle physics community in late 2023. "The Higgs field appears to have memory. It remembers previous high-energy interactions and responds differently to subsequent ones." This quantum memory effect suggested that even at maximum entropy, when all macroscopic activity has ceased and temperature approaches absolute zero, the universe might retain information about its history encoded in the most fundamental quantum fields. The implications were staggering. Absolute darkness might not mean absolute emptiness, but rather a state where information itself becomes the only remaining form of cosmic activity. And parallel discoveries at the Quantum AI Laboratory run by Google confirmed that quantum information could survive thermal equilibrium under specific conditions. Their 70-qubit Sycamore processor demonstrated quantum error correction that persisted even when the system was cooled to millikelvin temperatures, just thousandths of a degree above absolute zero NDR. Hartmut Neven, director of Google Quantum AI, realized the cosmological implications immediately. If quantum information can maintain coherence at temperatures approaching absolute zero, then the universe's approach to heat death might not eliminate information processing entirely. There could be quantum processes continuing even in the dark era. NTHE revelation that quantum coherence could persist indefinitely at low temperatures fundamentally altered models of cosmic death. Traditional heat death scenarios assumed that all organized activity would cease when thermal energy became insufficient to drive macroscopic processes. But quantum mechanics suggested that information processing might continue at the most fundamental level, invisible to classical physics but nonetheless real. NTHE 21st century's most profound revision to cosmic death theory emerged from the intersection of quantum mechanics, information theory, and cosmology. What scientists discovered was that the approach to absolute darkness was far more complex than classical thermodynamics had predicted, involving previously unknown forms of order that could persist even at maximum entropy, NDR. John Preskill of the California Institute of Technology led the theoretical development of quantum thermodynamics, a framework that extended classical entropy concepts to quantum systems. Preskill's work showed that quantum entanglement could create correlations between particles that persisted even when those particles were separated by cosmic distances. Classical entropy measures the disorder of classical information, Preskill explained in his landmark 2024 paper. But quantum entropy includes entanglement correlations that don't contribute to thermal disorder. A universe at maximum classical entropy could still possess enormous quantum order. NTHE mathematical formulation was precise. While classical entropy would indeed reach its maximum value when the universe achieved thermal equilibrium, quantum entropy could continue increasing indefinitely through the spontaneous generation of entangled particle pairs from vacuum fluctuations. These pairs would be created with zero net energy, but maximum quantum correlation, adding information to the universe without violating conservation laws. An experimental verification came from the Quantum Network Project, an international collaboration linking quantum computers across multiple continents. In 2025, the network demonstrated that quantum entanglement between laboratory systems remained stable, even when those systems were cooled to nano-Kelvin temperatures, just billionths of a degree above absolute zero (NDR). Ronald Hansen of Delft University of Technology, the project's coordinator, observed, "We're maintaining quantum correlations at temperatures that approximate the cosmic environment 10 to the power of 100 years from now. The entanglement doesn't care about temperature. It persists even in conditions that would represent absolute darkness in classical terms." NTHE implications for cosmic evolution were revolutionary. Instead of ending in perfect equilibrium, the universe's journey toward absolute darkness would involve an eternal increase in quantum complexity. The dark era wouldn't be empty. It would be filled with an ever-growing network of quantum correlations linking every particle in existence. This discovery resolved the black hole information paradox in unexpected ways. As black holes evaporated through Hawking radiation, the information they contained wasn't destroyed, but rather encoded in quantum entanglements between the emitted particles. The correlations would persist even after the black holes completely disappeared, preserving information about everything that had ever fallen into them. Dr. Ahmed Almheri of New York University calculated the implications. Every black hole that evaporates leaves behind a permanent record encoded in quantum entanglements. The universe is building a complete quantum memory of its own history. Maximum entropy doesn't mean maximum ignorance. It means maximum information storage capacity. The Planck collaboration's final data release in 2024 provided observational support for quantum cosmic evolution. Analysis of the cosmic microwave background's polarization patterns revealed subtle correlations that could only be explained by primordial quantum entanglements stretching across the observable universe. These correlations had survived 13.8 billion years of cosmic expansion and showed no signs of decay. Dr. Sylvia Galli of the Institut d'Astrophysique de Paris noted, "We're detecting quantum information from the first moments after the Big Bang, still encoded in the cosmic background radiation. If quantum correlations can survive since the beginning of time, they'll certainly persist until its end." As the scientific community absorbed the implications of quantum cosmic evolution, a new understanding of universal fate emerged that was both more complex and more hopeful than previous models had suggested. The universe's journey toward absolute darkness would not be a simple decay into emptiness, but rather a transformation into something unprecedented. A vast quantum computer processing information about its own existence. NTHE theoretical framework was developed by a consortium of physicists, computer scientists, and cosmologists, working under the auspices of the Foundational Questions Institute. Their 2025 report, Cosmic Information Processing in the Dark Era, presented the first comprehensive model of universe's computer scenarios. NTHE calculations were breathtaking in scope. A universe at maximum thermal entropy would contain approximately 10 to the power of 120 bits of classical information, the theoretical maximum for a finite region of space. But the same universe could store nearly unlimited quantum information through entanglement correlations, effectively becoming a cosmic-scale quantum computer with processing capabilities that dwarfed anything possible in the classical realm, NDR. Seth Lloyd of MIT, who pioneered quantum computing theory, provided the essential insight. Information processing doesn't require high temperatures or dense matter. Some of the most efficient quantum algorithms run best in cold, sparse environments. The dark era might be the universe's most computationally productive period. NTHE quantum computer universe would process information at temperatures approaching absolute zero, using energy provided by vacuum fluctuations, the irreducible quantum activity that persists even in empty space. These zero-point fluctuations, predicted by quantum field theory and confirmed by countless experiments, would provide sufficient energy to maintain quantum coherence indefinitely. Computer simulations of cosmic quantum evolution, run on IBM's quantum computers and Google's quantum AI systems, suggested that the processing capabilities would increase exponentially with time. As the universe expanded and cooled, quantum decoherence rates would decrease, allowing more complex quantum algorithms to run for longer periods without interruption. The possibilities were almost unimaginable. A quantum computer the size of the observable universe, operating for 10 to the power of 100 years or more, could simulate alternative histories, explore counterfactual universes, and perhaps even generate new forms of consciousness adapted to the quantum realm. The approach to absolute darkness would not be an ending but a transformation, the universe evolving from a classical physics system into a quantum information processing network of unprecedented sophistication. Observational evidence for cosmic quantum processing began appearing in data from the James Webb Space Telescope. Webb's infrared observations of the cosmic web, the largest structures in the universe, revealed correlations in the distribution of dark matter that appeared to follow quantum computational patterns rather than classical gravitational dynamics. Dr. Priyamvada Natarajan of Yale University, analyzing Webb's large-scale structure data, reported, "We're seeing organization in the cosmic web that looks suspiciously like the output of quantum algorithms. It's as if the universe is already learning to compute with itself." The discovery of cosmic quantum computation provided new answers to fundamental questions about consciousness and meaning in a mortal universe. If the universe could process information at the quantum level indefinitely, then perhaps consciousness, understood as a particular type of information processing, could persist in new forms adapted to the quantum environment. Dr. Chiara Marletto of Oxford University, working at the intersection of quantum theory and biology, proposed that quantum consciousness might emerge naturally in the dark era. Consciousness is fundamentally about information integration and processing. If the universe becomes a vast quantum computer, then forms of consciousness far more sophisticated than biological minds might spontaneously emerge. NTHE implications extended to the preservation of knowledge and culture across cosmic time. Everything that had ever been known, thought, or experienced could potentially be encoded in the universe's quantum memory, accessible to future quantum minds that might arise billions of years after the last star had died. NBUT. Even these quantum theories couldn't entirely escape the constraints of physics. The second law of thermodynamics still applied at the classical level, ensuring that macroscopic order would continue to decrease even as quantum information increased. The universe would still approach a state of maximum thermal entropy, even if that state contained unlimited quantum complexity. By 2026, humanity's most sophisticated instruments were providing direct measurements of cosmic death processes with unprecedented precision. Each observation brought clearer focus to the universe's ultimate fate while simultaneously revealing new layers of complexity that earlier theories had never anticipated. NTHE Extremely Large Telescope (ELT), first light achieved in 2028, began the most detailed study of stellar death ever attempted. With its 39-meter primary mirror, the ELT could observe individual white dwarf stars in galaxies billions of light-years away, directly measuring their cooling rates and confirming theoretical predictions of stellar death timelines. Dr. Roberto Gilmozzi, ELT project scientist, reported the first results. "We can now watch stars die in real time across cosmic history. The cooling curves match our models perfectly. White dwarfs are indeed approaching absolute zero at exactly the predicted rate." NTHEELT's observations revealed that approximately 95% of all stars that would ever exist had already been born. The universe was in its final star-forming phase, with most galaxies having exhausted their reserves of star-making gas. The transition to the degenerate era, dominated by stellar remnants rather than active stars, was already well underway. More disturbing were the ELT's observations of accelerated galactic dispersal. Dark energy's expansion was pulling galaxies apart faster than earlier measurements had indicated. The local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller galaxies, would remain gravitationally bound, but most other galaxies were already receding beyond the cosmic event horizon. Their light redshifted into invisibility. NTHE Cosmic Microwave Background Stage 4 experiment, fully operational by 2029, achieved the most precise measurements of cosmic temperature ever attempted. Using over 500,000 superconducting detectors deployed across Antarctica and Chile, CMBS-4 could measure the universe's background temperature to microkelvin precision. NTHE results confirmed that cosmic cooling was proceeding exactly as predicted by Big Bang cosmology. The current temperature of 2.725 Kelvin was decreasing at a rate of approximately 10 to the power of -9 Kelvin per year due to cosmic expansion. Extrapolating this rate forward, the universe would cool to within 1 Kelvin of absolute zero in approximately 10 to the power of 12 years, still unimaginably distant, but finite, NDR. Bradford Benson of Fermilab, CMBS-4's principal investigator, observed, "We're measuring cosmic death with the same precision that we measure the temperature of a human body. The universe has a fever of 2.7 degrees above absolute zero, and we can track its decline year by year." NTHE High Luminosity Large Hadron Collider, achieving full operational capacity in 2030, provided definitive measurements of vacuum stability. Analysis of Higgs boson self-interactions confirmed that the universe exists in a metastable vacuum state, with a lifetime approximately equal to the current age of the universe, multiplied by 10 to the power of 100 NDR. Fabiola Giannati, CERN Director General, announced the implications. The universe is stable on timescales comparable to classical heat death, but vulnerable to quantum tunneling on longer timescales. We're safe from vacuum decay for 10 to the power of 100 years, but not forever. The measurements reveal that vacuum decay, if it occurred, would propagate at light speed in an expanding universe, meaning it could never catch up with regions of space receding faster than light due to cosmic expansion. This provided a possible escape route. Parts of the universe might remain in the false vacuum indefinitely, preserving familiar physics even if other regions transition to different vacuum states. Breakthrough. Listen, the most comprehensive search for extraterrestrial intelligence ever conducted, announced its final results in 2030 after scanning over 1 million stars in our galaxy. The project had found no evidence of technological civilizations beyond Earth, despite achieving sensitivity levels that could detect transmissions from technologies far more advanced than our own. Dr. Andrew Simeon, Breakthrough Listen Director, reflected on the implications. The silence suggests that technological civilizations are extremely rare, or that they face insurmountable challenges that prevent them from becoming cosmic-scale communicators. We may be alone in confronting the universe's mortality. NTHE discovery of cosmic solitude added poignancy to humanity's growing understanding of universal fate. If consciousness was indeed rare in the cosmos, then the knowledge we had gained about cosmic death might be among the universe's most precious and fragile achievements, perhaps the only understanding the universe would ever have of its own mortality. Gravitational wave astronomy reached maturity with the completion of the Einstein telescope in 2035. The third-generation detector achieved sensitivity levels sufficient to observe the gravitational radiation from evaporating black holes, the first direct detection of Hawking radiation through its gravitational effects. NTHE observations confirmed Stephen Hawking's 1974 predictions with extraordinary precision. Black holes were indeed evaporating at exactly the predicted rate, converting their mass into thermal radiation and gravitational waves. The most massive black holes in the universe would take approximately 10 to the power of 100 years to evaporate completely, defining the transition from the black hole era to the dark era, NDR. Gabriela Gonzalez of Louisiana State University Einstein Telescope Project scientist observed, "We're watching the universe's final energy sources slowly disappear. Every detection confirms that we're in the late stages of cosmic evolution, approaching the era when only quantum processes will remain active." NSP-ACE-based observations reached their ultimate expression with the deployment of the Cosmic Webb Observatory in 2038, a network of telescopes positioned throughout the outer solar system to measure the universe's large-scale structure with unprecedented resolution. The observatory's measurements revealed that dark energy constituted exactly 68.47% of cosmic energy density, with an equation of state parameter W equals -1.003 plus or minus 0.001. NTHE precision measurement confirmed that dark energy was extremely close to, but not exactly, Einstein's cosmological constant. The small deviation from W equals -1 suggested that phantom dark energy was indeed present, but so weak that the Big Rip would occur in approximately 120 billion years rather than the 22 billion years predicted by stronger phantom energy models. Dr. Rachel Mandelbaum of Carnegie Mellon University, the observatory's chief scientist, announced, "We now know the universe's fate with unprecedented precision. We have about 120 billion years before dark energy tears apart the fundamental structure of space and time." As humanity's instruments achieved their ultimate sensitivity and precision, measuring cosmic death with accuracy previously thought impossible, a profound philosophical reckoning emerged. The universe's mortality was no longer theoretical speculation but established scientific fact, confirmed by multiple independent observations, and verified through decades of precise measurements. NTHE implications reached far beyond physics and astronomy. Every human institution, every cultural achievement, every work of art and literature, every act of love and creation, existed against the backdrop of cosmic mortality. The universe that had given rise to consciousness was itself mortal, and consciousness had become aware of this mortality with scientific precision. Dr. Carlo Rovelli of the Centre de Physique Théorique in Marseille captured the existential dimension. We are the universe becoming conscious of its own mortality. In developing science, consciousness has given the cosmos a way to understand its own death. This is perhaps the most poignant achievement possible. Knowledge that transcends the knower. The concept of cosmic mortality transformed human perspectives on meaning and purpose. If the universe itself was temporary, then all achievements within it shared that temporality. Yet this didn't diminish their significance. It might actually enhance it. Beautiful and meaningful events became more precious precisely because they occurred within a mortal cosmos. Religious and philosophical traditions grappled with the implications of scientifically confirmed cosmic death. Some found in the finite universe a poignancy that made existence more, not less, meaningful. Others struggled to maintain concepts of eternal significance in a universe heading toward maximum entropy. NTHE Dalai Lama, in his 2035 address to the International Astronomical Union, offered a Buddhist perspective. The universe's impermanence is consistent with fundamental Buddhist understanding. That all phenomena are temporary does not make them less real or less worthy of compassion. Perhaps cosmic mortality teaches us that the present moment, this moment of awareness, this moment of love, is infinitely precious, precisely because it will not last forever. Pope Francis III, addressing the Vatican Observatory's 2036 Conference on Cosmology and Faith, provided a Christian interpretation. If God created a mortal universe, then mortality itself is holy. The journey toward cosmic death may be the universe's way of returning to its creator, completing a divine cycle that transcends our current understanding. Secular philosophers developed new frameworks for meaning in a mortal universe. Dr. Rebecca Neuberger Goldstein of Rutgers University proposed cosmic humanism, the idea that human consciousness represented the universe's attempt to understand itself, making each moment of awareness a cosmic achievement. We are not separate from the universe observing it from outside. Goldstein wrote in her influential 2037 book, The Mortal Cosmos, "We are the universe observing itself from within. Our consciousness is cosmic consciousness. Our mortality is cosmic mortality, and our understanding of cosmic death is the universe's understanding of its own fate." NTHE artistic community responded with extraordinary creativity to the revelation of cosmic mortality. The entropic movement in visual arts explored themes of cosmic death through installations that evolved and decayed over time, mirroring the universe's approach to maximum entropy. Musicians composed deep time symphonies that would take centuries to perform, creating musical experiences spanning multiple human generations. Literature grappled with the challenge of narrating meaning within cosmic mortality. The Nobel Prize in Literature for 2038 was awarded to Kim Stanley Robinson for his novel The Dark Era, which imagined consciousness persisting in quantum form long after the last stars had died, finding beauty and meaning in the subtle information processing of a universe at maximum entropy. Scientists themselves found that studying cosmic death paradoxically enhanced rather than diminished their sense of wonder. Dr. Catherine Fries of the University of Texas, author of the definitive textbook, The Physics of Cosmic Death, observed, "Understanding how the universe will end makes me appreciate how extraordinary it is that we exist at all. We live in the universe's most creative period, when complexity and consciousness are possible. That makes every moment of awareness a miracle." The educational implications were profound. Children growing up in the 2040s learned about cosmic mortality as naturally as they learned about biological mortality. Rather than creating existential despair, this knowledge seemed to foster a deeper appreciation for the present moment and a stronger commitment to preserving knowledge and culture across cosmic time. NDR. Neil deGrasse Tyson, in his final lecture before retirement in 2040, reflected on humanity's journey toward understanding cosmic death. "We began this quest thinking we were learning about the universe's fate. What we discovered is that we were learning about our own significance. In a mortal cosmos, consciousness is not an accident. It is the universe's way of witnessing its own extraordinary existence." In the final analysis, the discovery of cosmic mortality, scientifically confirmed through decades of precise observation and measurement, revealed something unexpected about the relationship between consciousness and cosmos. Far from rendering existence meaningless, the universe's finite lifetime elevated consciousness to cosmic significance. The numbers were now known with unprecedented precision. The universe would continue creating stars for approximately 100 trillion years, though at an ever-decreasing rate. The last red dwarf stars would burn out after 10 trillion years. The last white dwarfs would cool to near absolute zero after 10 to the power of 15 years. Proton decay would eliminate all atomic matter by 10 to the power of 40 years. The final black holes would evaporate through Hawking radiation by 10 to the power of 100 years. NBUT quantum information processing would continue indefinitely, powered by vacuum fluctuations and organized through entanglement correlations that could persist forever. The dark era would not be empty. It would be filled with quantum computation on cosmic scales, possibly giving rise to new forms of consciousness adapted to the quantum realm. Dr. David Deutsch of Oxford University, quantum computation pioneer, offered the ultimate perspective. The universe is not dying, it is transforming. Classical physics gives way to quantum information processing. Biological consciousness may evolve into quantum consciousness. The approach to absolute darkness is not an ending but a metamorphosis. The timeline stretched before humanity with mathematical precision. The current era of stars and planets would last another 100 trillion years, a period 10 million times longer than the universe had already existed. Consciousness had time not just to survive, but to evolve into forms currently unimaginable. Yet the knowledge of cosmic mortality gave urgency to the present moment. This era, when complexity and consciousness coexisted with stellar energy sources, might be unique in cosmic history. The thoughts thinking themselves in human minds, the emotions experienced in human hearts, the beauty perceived in human consciousness, might be rare and precious phenomena in the cosmos's 10 to the power of 100-year journey toward maximum entropy. the universe had become aware of its own mortality through human consciousness. In the brief span of a few thousand years, human science had progressed from believing in an eternal, unchanging cosmos to precisely measuring its rate of cooling toward absolute zero. This achievement represented the universe's development of self-awareness, the cosmos understanding its own nature through the consciousness it had produced. NTHE final poetic truth was that consciousness and cosmos shared the same fate. Both were temporary phenomena in the universe's evolution from low entropy to maximum entropy. But their temporality didn't diminish their significance, it revealed their cosmic importance. In a universe heading toward absolute darkness, every moment of awareness was a triumph over entropy. Every conscious thought was a victory of order over disorder. NTHE approach to absolute darkness would take 10 to the power of 100 years to complete. But consciousness existed now, in this moment, aware of both its own significance and its own mortality. In the vast sweep of cosmic time, from the Big Bang to the Dark Era, consciousness represented the universe's brief but extraordinary experiment with self-awareness. Perhaps this was the ultimate meaning of cosmic mortality. Not that consciousness was insignificant in an indifferent universe, but that consciousness was the universe's way of giving significance to itself. The journey toward absolute darkness would be long and complex, involving transformations currently beyond imagination. But it would be witnessed, understood, and perhaps even guided by the consciousness that the universe had created to know itself. In the end, the universe's mortality became not a source of despair, but a source of wonder. We existed at exactly the right time, in exactly the right place, with exactly the right kind of consciousness to understand our cosmic situation. The privilege of awareness, the democracy of darkness, the beauty of finite existence, these became the themes of a new cosmic philosophy that found meaning not despite universal mortality, but because of it. NTHE universe was mortal. Consciousness was mortal. But in the brief time when both existed together, something extraordinary had occurred. The cosmos had become aware of its own beauty, its own complexity, and yes, its own mortality. That awareness itself might be the most significant event in the entire 10 to the power of 100-year history of cosmic evolution. The moment when the universe opened its eyes, looked at itself, and found both meaning and mystery in what it saw. As the cosmic microwave background radiation continued its 13.8 billion-year journey toward absolute zero, as dark energy continued to accelerate the expansion of space, as the final black holes began their long evaporation toward nothingness, consciousness remained, for now, to witness, to understand, and to find beauty in the extraordinary fact that in a universe heading toward absolute darkness, there had been for just a moment in cosmic time the light of a